Am I audible? Noha, Yashika, Minashi, am I audible?
Yes, sir.
Good evening, sir.
Bhishma, you were absent in the last class, huh?
Yes, sir.
Okay, so in the last class, we have finished potential energy. The last topic of potential energy was potential energy of dipole in a uniform electric field. This we have finished. After potential energy of dipole, the next topic is conductors. The next topic is conductors. So, what are conductors? So, conductors are those materials which have free electrons. Conductors, they have free electrons. So, conductors are material which can conduct electricity. And what's so special about the conductors? Conductors have free electrons. They have free electrons. Which helps in conduction. Which helps in conduction. So if you take a particular conductor, let's say if you take a cylindrical conductor, then this cylindrical conductor have, let's say you take a conductor of copper. Then this copper conductor will have two particles of interest. One is ions. One is ions. Positively charged ions and free electrons. Free electrons. So conductor have free electrons and positively charged. So this is positively charged ion and free electrons. These ions are immobile. They can't move from one point to another. Ions are immobile. But electrons are free to move throughout the body of conductor. They are free. Free. So these are conductors. They have immobile ions and free electrons, which are responsible for their conduction. Now, conductors have some very special properties. The first property is charge inside a conductor is always zero. If you give charge to a conductor, then that charge will reside only on the outer surface. Net charge inside a conductor is always zero. So you can say charge inside a conductor is always zero. Is always zero. So there is no charge inside the conductor. Charge resides only on the outer surface. Charge resides only on the outer surface. Only on the outer surface. So net charge inside a conductor is zero. Charge will reside only on the outer surface of the outer surface of conductor. So if you take a conductor, it could be a hollow conductor, it could be a solid conductor. Even if this conductor is solid, the charge inside will be zero. Charge will reside only on the outer surface. So can I use volume charge density for a conductor, or I should use only the surface one? Yes, charge inside a conductor is 0. So I'm saying, can I use volume charge density for a conductor? Or should I always use the surface charge density only? Minashi.
Sir, surface charge density.
Surface charge density. There is no charge inside the conductor, so we can't use volume charge density. We always use surface charge density for the conductor. Surface charge. Second problem. If you take a conductor, then electric field inside a conductor is 0. Electric field inside a conductor is 0. So if there is no charge, that means no field. So if you have a conductor, then inside the conductor, the field is 0. There is no field inside. So if you take a conductor, then field inside will be 0. We have already proved this result for a solid conducting sphere. When we were doing applications of Gauss law, then we have discussed this result, that electric field inside the conductor. But since charge resides on the outer surface, you will have some field on the outer surface. So electric field.
Excuse me, sir.
Yes, sir.
Sir, can you brief it all again, sir? I didn't understand anything.
I'm just repeating. Just give me. So electric field resides. Okay, I'm just repeating. So we start with conductors. What are conductors? Conductors are materials which can conduct electricity. What's so special about the conductors? Conductors have free electrons. So if you look at a conductor, let's say if you look at a piece of copper, then that copper piece have two things of interest. One is ions, copper ions, which are immobile. Copper ions cannot move. And they also have electrons, free electrons. Electrons are free to move within the body of conductor. Like if you take a conducting wire of copper, then the free electrons can move throughout the wire.
Okay, sir.
So we have few properties of conductor. Due to these free electrons, conductors have some very special properties. The first property is you will not find any charge inside the conductor. Charge inside the conductor is always 0. Whatever charge you have, that will reside only on the outer surface. No charge inside the conductor. Second property. Electric field inside a conductor is 0. There's no field inside the conductor. Third, electric field is always perpendicular.
Sir, what were that immobile structure that you made?
Immobile means they can't move. See, the ions are heavy, right? As compared to electrons, the copper ions are very heavy ions. They can't move like free electrons. That's why I'm writing immobile ions. They can't move. They are not mobile. But electrons can move freely throughout the body. Electric field is perpendicular to the surface of conductor. Its value is sigma by epsilon. This is the value of electric field on the surface of conductor. It is always perpendicular to the surface and value is sigma by epsilon. This is the field on the surface. So if you take a conductor, so if I take a conductor of some arbitrary shape, then electric field is always perpendicular to the surface. And the value of field is sigma by epsilon. This is it. Fourth. This we have already proved when we were doing Gauss law. So I'm not repeating these results again. We have proved this result for a sphere, a conducting sphere, solid conducting sphere. Last property is for potential. Electric potential electric potential is constant throughout the body of conductor. Throughout the body of conductor. It has same value on surface as inside. Like if you take a conductor, let's say this is a conductor. Electric potential is constant throughout the body. Like if on the surface, I give some charge to this conductor. If I say that potential on the surface is plus 2 volt, then inside the conductor is potential plus 2. So throughout the body of conductor, potential has same value. This is the last property. So using these, yes.
Sir, but you earlier told that it only existed on surfaces, not inside the conductor.
Field exists on the surface, not potential. The property was regarding field and charge, right? I'm writing potential. Potential
Okay,
is
sir, got it.
throughout the body. It has same value inside the conductor as on the surface. Fifth is electrostatic shield. Electrostatic shield. Electrostatic shielding means if you want to say you have some very delicate device and you want to put that device in a region which does not have electric field. You have a device and you want to place that device into a region which does not have electric field. So then you will need some region which does not have electric field. Then that region is conductor. So if you take a conductor, space inside the conductor is free of all types of electrical influence. There is no charge inside the conductor. There is no field inside the conductor. The space inside the conductor is free of all types of electrical influence. Whatever charge configuration you have exists only on the surface. Field exists only on the surface, nothing inside the conductor. This is known as electrostatic shield. That space inside the conductor is independent of all types of electrical influence. Space inside conductor is free of all electrical This is what we call electrostatic shield. Electrostatic shielding means inside the conductor there is nothing, neither charge nor field. Space inside the conductor is free of all electric influences. So these are the following 5 properties of it. The first property is they have free electrons, which are responsible for their electrical conductivity and these properties. Just note it down and tell me if you have doubts. Raj, clear?
Yes, sir.
See, Alia, the point 5 says space inside a conductor is shielded from all types of electrical influences. Means if you take a conductor and you give charge to the conductor, then charge will reside only on the outer surface, not inside the conductor. Space inside the conductor is free of charge. space inside the conductor is free of electric field. There can't be any electric field inside the conductor. If you apply any field, then that field will exist only on the outer surface, not inside. That is electrostatic shield. Space inside the conductor is free of all types of electrical influence. No charge, no field inside. Ishma, is it clear?
Yes, sir.
Ishma, this topic is independent of last lecture. In the last lecture, we finished potential energy. We won't be using potential energy in this class.
Okay.
First, we'll do conductors, then we will start capacitors. Mazia, written. Mazia, use your chat room at least. Anshika, can I scroll it further?
Yes.
Mazia, written.
Sir,
Yes, Arpit.
can you explain what is surface charge density?
Charge per unit area.
Okay, sir.
Charge per unit area. It's charge upon area. We have three types of continuous charge distribution: the line charge, surface charge, volume charge.
Yes, sir. got it.
Surface charge. Any doubt, Mazia, in these 5 points? Can I scroll it? No. Yes, written.
Yes, so
So the next is electric potential due to a hollow conducting, non-conducting, or a solid conducting sphere. See, this particular topic is not in the CBSE syllabus for 2022. But without this topic, we can't do capacitance. So for doing capacitance, you should know how to calculate potential and one simple numerical law. So I'm not going through the derivation. So you have a sphere. The radius of the sphere is R. We provide some charge Q, to the sphere. Now you have to calculate potential at 3 points. At point A, which is outside the sphere. You need potential B on the surface of sphere. And you need potential at point C, which is inside the sphere. Separation between the center of the sphere and point A is R. So potential outside the sphere is simply same as that of a point charge. 1 over 4 pi epsilon naught. It's Q by R. Potential on the surface of the sphere have same value as that of a point charge. 1 over 4 pi epsilon naught Q by R. Outside the sphere. When you calculate potential on the surface of sphere, Anshika, what will be the value for the surface? The radius of the cylinder or the sphere is capital R.
So 1 by 4 epsilon naught Q by capital R.
Q by capital R, it's 1 over 4 pi epsilon naught. It's charge Q divided by radius capital R. This is potential on the surface. Next, you need potential inside the sphere. So when we calculate potential inside the sphere, potential inside the sphere is same as that on the surface. So which is 1 over 4 pi epsilon naught, it's Q by R. So when you take a sphere, it could be a hollow conducting, it could be a solid conducting, or it could be a non-conducting hollow sphere. Potential outside the sphere is 1 over 4 pi epsilon naught Q by R, where R is the separation between the center of the sphere and this point. Surface, it's Q by the radius of the sphere. And inside the sphere, potential is same as that on the surface. Now the next task is to plot potential versus position graph. Let's say this is R equal to capital R. R equal to capital R means surface. This point lies on the surface. Then you have R less than capital R. This point is inside the sphere. Then you have R greater than capital R. This is the point which is outside the sphere. And this is R equal to 0, which is center. Hishma, what is the value of potential at the center of the sphere? Hishma, value of potential at the center of the sphere. Alia, potential on the center of sphere. No.
So 1 by 4 pi epsilon naught Q.
Q and by R, right? See, inside the sphere, potential is same as that on the surface. That means even at the center, the value of potential is same as that of the surface. So this is the value at the center, which is V surface. And what is the value of potential in this region? R is less than capital R. Arpit? Expression for potential for this region, R is less than capital R. Arpit? Miraj, potential in this region, R is less than capital R. What's the value of potential in this region?
Sir, it will be, sir, it will be 1 by 4 pi epsilon naught dot Q by dot Q by small r.
Small r. Yashika, what will be the value of potential for this region? R is less than capital R. Yashika. Noha, value of potential inside the sphere.
So 1 by 4 pi epsilon naught into Q upon
Capital R. So the value is same as that on the center. See, inside potential is same as that of the surface, right? So when I say inside, then inside it could be center, it could be any point inside the sphere. Inside the sphere, the value of potential is same, 1 over 4 pi epsilon naught Q by R. So the graph will remain a straight line. If you calculate potential at the center, then it's Q by R. If you calculate at any point inside the sphere, it will remain 1 over 4 pi epsilon naught Q by R. But when you calculate potential outside the sphere, it goes as 1. Outside, it goes as 1. So V out is inversely proportional. So if, for example, like if I give you a sphere and I say that potential here is 2 volt, Then what will be the value of potential here, Minashi?
Plus
At
2V.
center, it's 2 volt. This will be
Plus 2V.
plus 2V. And what about potential here?
Plus 2V.
And what about here? It will be plus 2, greater than plus 2, less than plus 2.
Would be less.
It would be less because when you go outside the sphere, potential decreases with separation. So it will be less than 2. So this is what this graph is telling. This graph is telling that from center to the surface, potential is not changing. But when you go outside, potential varies as 1 by r. Is it clear, everyone?
Yes, sir.
Jashika?
Yes, sir.
Yes, sir.
Okay, just note it down. Do one numerical. Tell me once you have written. We'll do one numerical, one simple numerical on this concept.
So can you slow? Can you scroll it?
Sir.
Okay, let's do one question based on this concept. Yes, everyone have written? Noha, Yashika, Anshika.
Yes.
Yes, sir.
So the question is, you have two spheres. Huh? You have one sphere. The radius of this sphere is A. And the charge on this sphere is Q1. This is a positively charged sphere. This have some charge. Around this sphere, you have another sphere. Charge over this sphere is Q2. Radius of the sphere is. I need to calculate potential at following points. Like I need potential at point, let's say this is A, and I need potential at point. Let's do it here. So when I calculate potential at point A, then potential at point A will have contribution from both the spheres, sphere 1 as well as sphere 2. Sphere 1 will generate potential at A as well as sphere 2 will also generate potential at A. So potential at A is potential due to sphere 1 plus potential due to sphere 2. Hishma, for sphere 1, what is the location of point A? This is at the surface, inside, outside. What is the location of point A? Hishma.
The second you
Inside
repeat.
this.
Inside, right? For Q1, where is point A, Hishma? Inside?
On the surface.
On the surface. Minashi, for this charge Q2, what is the location of point A? Inside, outside, surface?
For Q2
Yes, due to Q2.
on the surface.
Where is this point A? Not B, A.
Inside the
Inside.
surface.
Sorry?
Inside the surface.
Inside
Inside
the
the sphere.
sphere. So you need potential at point A. Potential at point A is due to two spheres. Sphere 1 having charge Q1. For sphere 1, the point is on the surface. For sphere 2, the point is inside. So when you calculate this potential, what's the formula of V1 on the surface, Anshika? You do Q1, you need
So
potential.
1 by
Huh?
1
Yes.
by 4 pi epsilon naught Q by 8.
Q by, very good. Q1 by, right?
Yes.
Noha, what is the expression of potential due to sphere 2, Q2 at point A? Noha.
So Q2 upon 4 pi epsilon naught B.
B. Why B? Because potential at the surface is equal to potential inside the sphere. Say you need potential inside the sphere, but potential inside the sphere is equal to the value of potential at the surface. So that's why we will use 1 over 4 pi epsilon naught Q2 divided by. Clear? Similarly, I need potential at point B. So for potential at point B, so both Q1 and Q2 will contribute to the potential at B. So when you calculate potential at B, will have contribution from both B1 as well as B2. Alia, for this charge Q1, for the first sphere, what is the location of point B? Inside, outside, surface? Inside.
Outside.
Outside. Now see, this is the sphere. This is charge and this is the point. For this sphere, where is this point? Inside or outside? Alia. See, check point with respect to charge. See, this is the charge, this is the sphere, and this is the point. This point lies outside the sphere, so outside. And what about the second sphere Q2? Yashika, what is the location of D with respect to Q2 inside outside surface?
On the surface.
On this. So that is V2 surface. So what is the expression of potential V1 outside? For this Q1, potential outside is 1 over 4 pi epsilon naught charge Q1 divided by. What you will write in denominator, Alia? What you will write in denominator? A, B, R, what you will write? Alia, what will be the missing term?
A.
A. Yashika, what will be the missing term? A.
Sir, B.
B. You're calculating potential at B, na? So you need center separation between center to center separation. So from center to center separation is B. You need separation from the center of the sphere to the point. Right? So due to first sphere, you are calculating potential at B. For first sphere, B is outside. This is sphere and this is point. For potential, you need 1 over 4 pi epsilon naught Q by R. What is R? R is the separation between the center of the sphere and the point. Separation between center of sphere and point is B. So we'll write this as plus V2 surface. So it's 1 over 4 pi epsilon naught. Charge is Q2. And this is the separation, center to center separation is B again. No, you are calculating potential on the surface. So potential on the surface of the sphere is charge divided by the radius of this. This is V. When you compare VA and VB, when you compare VA and VB, you will find that VA is always at higher potential with respect to V. Inner sphere is always at higher potential with respect to V. So inner sphere is always at higher potential with respect to. This statement is also known as principle of Venn diagram generator. There was a device in your syllabus. Its name was Venn diagram generator. Principle of Venn diagram generator. Do it. So principle of Venn diagram generator simply means if you take two concentric spheres, then inner sphere is always at a higher potential with respect to the outer sphere. This is the principle of Venn diagram generator. That inner sphere is always at a higher potential with respect to the outer sphere. Yes, sir. I will share. At the end of the class, I will share.
Okay, sir.
Is it clear? Minashi, Rishma, Yashika?
Yes, sir.
Okay, so after conductor, the next topic is capacitance. Let's start with capacitance. So what is capacitance? Capacitance is nothing but charge holding capacity of a conductor. Charge holding capacity of a conductor. Charge holding capacity of a conductor is known as capacitance. See, if you take a conductor of any arbitrary shape and size, so there's a maximum amount of charge that you can give this conductor. If you exceed that limit, then charge will start leaking from the conductor. So the maximum amount of charge that you can provide a conductor is fixed. And the capacity of conductor is controlled by capacitance, charge holding capacity of conductor. So greater the capacitance of a conductor, greater is the amount of charge that it can store. So capacitance is simply charge holding capacity of a conductor. So if you take a conductor, you provide some charge Q to the conductor. The potential on the surface of conductor is V. So when you provide charge Q, Q is directly proportional to V. When you remove this sign of proportionality, you use a constant C. This C is what we call capacitance. This C is known as capacitance. You can write C as Q by V. So when you look at this relation, it feels like capacity is directly proportional to charge. Capacity is inversely proportional to potential. But actually, capacitance is independent of charge and potential. Because potential also depends upon charge. So when you divide Q by V, the dependency of charge gets cancelled out. So capacitance is independent of charge and potential. It depends on shape and size. It depends on only shape and size. So capacitance is independent of charge and potential. It depends only on the shape and size of conductor and medium. So when you calculate SI unit of capacitance, SI unit is charge by potential, SI unit of charge is coulomb, SI unit of potential is volt. So it's coulomb per volt, or you can say that SI unit is farad. SI unit of potential is farad. Capacitance is farad. But 1 farad is a very big unit. You can use some small units like 1 millifarad, which is 10 raised to the power minus 3 farad. Or you can use even a smaller unit, 1 microfarad, which is 10 raised to the power minus 6. Smaller. So when you plot, let's say you take capacitance, you take charge here and capacitance here. Capacitance is independent of charge. It does not vary with charge. So the graph will be parallel. You keep on changing the charge, capacitance will not change. Similarly, if you plot capacitance versus potential graph, it's independent of potential. It does not change with potential. So this is capacitance. Charge holding capacity of a conductor is capacitance. Greater the capacitance of the conductor, greater will be the charge holding capacity. So if you provide conductor charge more than its capacity, then that charge will leak to the environment. So if you take a conductor, you keep on supplying charge, then after a certain limit, that charge starts leaking from the surface of conductor in the environment, in the air. And this capacitance is just the ratio of charge and the potential. It's not long. Miraj, is it clear? Capacitance?
Yes.
Vishma? Any doubt?
No, sir.
Mazia? We'll calculate capacity of a sphere. We'll see how to calculate capacity of a sphere.
So, sir, can you scroll up a bit?
Okay, okay, Alia. Capacitance of an isolated sphere. Capacitance of a conducting sphere. So if you take a sphere, this is the sphere. Some charge Q is uniformly distributed on the surface of the sphere. The radius of the sphere is R, the conducting sphere. You have to calculate the capacitance of the sphere. So to calculate capacitance, we can first calculate the potential. So what is potential on the surface of sphere? Potential on surface of sphere. Yes, Bhishma, what is the value of potential on the surface of sphere?
1 by 4 pi epsilon naught q by.
Noah, what's the formula for calculating potential capacitance? Noah, relation for calculating capacitance.
Q upon V.
Q upon V. Let's call this as equation number 1 and this as equation number 2. So when you substitute 1 in 2, we get capacitance is Q by V. V is 1 over 4 pi epsilon naught. Q will cancel this Q and you will get C is 4 pi epsilon naught. So this is the capacitance of a sphere. See, this is independent of charge. There is no charge in this expression. It is independent of potential. No potential in this expression. It depends only over R, which is geometry, and epsilon naught, which depends upon medium. So this is the formula for capacitance of a sphere. So if you have an isolated sphere, then this is the potential. This is the capacitance, 4 pi epsilon. So if we consider Earth, to be a conducting sphere, then we can calculate the capacitance of Earth also. Capacitance of Earth will be 4 pi epsilon naught radius of Earth. So if I substitute all values, see, pi is 3.14, epsilon naught is 8.85 into 10 raised to the power minus 12. Radius of Earth is 6.4 into 10 raised power 6. And when you do all these calculations, you get 711 into 10 raised to the power minus 6, which is 7119. So this is the value of capacitance of Earth. So if you consider, or if you take a conductor of the size of Earth, then also its capacitance is just few microfarads. You can imagine 1 farad is a very, very big unit. Even a conductor of the size of Earth will have this much of capacity. So 1 farad is a very, very big unit in terms of capacity. So this is the method to calculate capacitance of any system. First calculate potential for that system and then take the ratio of charge and potential. The ratio of charge and potential will give you capacitance. It's not enough. Yes, written. Can I scroll it? Anshika, Arpit, Hishma. Written.
Yes, sir.
See, after this, the next question is not the question. The next is capacitors. See, why we need capacitors and what are capacitors? So see, if you take a conductor of the size of Earth, then also its capacity is very small. It is few microfarads. So if you want to store greater amount of charge, then you need a system which can store as much charge as you want. So that system is capacitor. It's a device used to store charge. The device that we use to store large amount of charge is known as capacitor. So a very small capacitor can hold more charge than the entire Earth. So if you take a conductor of the size of Earth, that conductor can hold a charge of 711 microfarad. You can have a very small capacitor that you usually use in your mobile phones also. That capacitor can hold charge comparable to the charge which hold by a conductor of the size of Earth. So it's a device which can store large amount of charge in a very small space. This is a device used to store charge. And how we obtain capacitor? It consists of two oppositively charged charged conductors separated by a dielectric medium. So what is capacitor? The simple device which we use to store charge. How to make a capacitor? Take two conductors. They should be separated by a dielectric medium. One of them should be positively charged. Another one should be negative. This is the system which we call capacitor. Two conductors having opposite charge separated by a dielectric medium. This is what we call capacitor. So you can have various types of capacitors. You can have parallel plate capacitor. You can have a spherical capacitor. You can have cylindrical capacitor. You can have capacitor of various shapes, parallel plates, spherical, cylindrical. These are the various shapes of capacitor. And this is the symbol of capacitor. This is how we represent capacitor. So what is capacitor? It's a simple device which we use to store large amount of charge. It consists of how to make a capacitor. You can take two plates, oppositively charged plates, and they should be separated by a dielectric medium. This is a capacitor. We have three types of mainly capacitors: parallel plate, spherical, and cylindrical capacitor. We solve this simple question. A charge of 10 coulomb is placed at the center of sphere. Calculate first part. Surface charge density of the sphere. Second, capacitance of sphere. The radius of the sphere is given. The radius of the sphere is 10 centimeter. At the center of the sphere, you placed a charge of 10 coulomb. Get the surface charge density and the capacitance of the sphere. Solve it. Ten coulomb charge at the center, radius of the sphere is 10 centimeter. Get the value of surface charge density and capacitance. Answers. See, you can start is the charge is at the center. So due to induction, this charge will come to the surface. So on surface, you have 10 coulomb of charge. Get the value of surface charge density and the capacitance. Answers. Minashi, are you solving it?
Yes, sir.
Not that lengthy. You can write your answer in terms of pi. Okay, I don't. No need to put pi as 3.14. You can calculate in terms of pi also. Jessica, done? Okay. Second part. Okay, Alia. I got just two answers, Yashika and Ali. Arpit, Anshika. Okay. Bhishma, Minashi, Arpit, answer. See, this is straightforward. So in the first part, surface charge density is charge over area. So the charge is plus 10 coulomb. It's just sphere area is 4 pi r square. Area of the sphere is 4 pi r square. So it's q over 4 pi r square. Substitute values. Q is 10 coulomb. It's 4 pi r. R is 10 centimeter, which is 10 raised to the power minus 1 square. So it comes out to be 10 raised to the power 3 by 4 pi coulomb per minute. This is sigma. Arpit? Arpit? No.
Yes, sir.
Second part. After surface charge density, you need capacitance. What's the formula for the capacitance of sphere, Ishma? Ishma, capacitance of sphere. 4 pi epsilon naught r. So that's 4 pi is 3.14. Epsilon naught is 8.85 into 10 raised to the power minus 12. Radius of the sphere is 10 centimeter, which means 0.1. This much of this is the capacitance of the sphere. 4 into 3.14 into 8.85. Do it. Okay, with this question, we'll stop today. We'll not start any new fresh topic now. We'll continue with capacitance of a parallel plate capacitor from the next class. From the next class, we'll be starting parallel plate capacitor. We'll stop it.
Thank you, sir.
Thank you, sir.